Alrighty guys, so here's a real example of how you might use exponential decay and growth. We have the number of oaks and birch trees since 1950 are shown below. Shown, Mr. Milano. So we have the following tables, and we want to create an equation for each one. So let's use some common sense here, guys. The oak, we're talking about the number of years it's going. Are you guys seeing that it's going by every 3 years? So we're adding 3 every single time. Now, in this other side, it's going to get a little confusing, guys, so bear with me. 34, from 34 to 46, how much are we adding? 34 to 46, isn't that, aren't we adding 12? Okay. From 46 to 59, isn't that plus 13? Let me double check, just play it safe here. Plus 13, yep. 59 to 70, isn't that plus 11? Yep. And the last one, plus 12. So notice here, guys, we're not really adding the same all the time. However, we want to be as close as possible. So for this lesson, the average, more or less, we're adding about 12 because it's the average. Over here, we know for a fact we're going by 13. So if you guys don't remember, y equals mx plus b, this is the formula we're going to be using because it's growing at the same rate. We're always adding the same thing to both sides, or like it's constant, if that makes sense. Well, remember, let's do a little quick review on this. Letter B is always going to be the y-intercept. That's when x is 0. And letter M is going to be the slope, the rise over the run. So in this case, we have y equals. Well, what was my rise, guys? How much was I adding to the branches? We were adding 12, plus 12, right? And how much were we adding to the years? Plus 3. So that's going to be the slope. The x stays there. And when x was 0, in this case, the years, what was my y? 34. There you have it. And if I were to simplify, guys, what's 12 divided by 3? That's 4x plus 34. There you have it. Now, over here, guys. So we know this is linear because the slope is constant. Now in this case, let's analyze this a little more. On the birch trees, we're going on the left side, we're going by tens, right? Plus 10, etc. On the other side, however, look at the numbers. The numbers are increasing way too fast. So obviously we're not adding, and we cannot deduce a similar addition to every single one. Just the numbers are way too crazy. So with that in mind, let's figure out by working backwards. Look, 2049. We know we're multiplying to get that number, but let's work backwards so we figure out the number before that. If we divided 2049 divided by 512, we actually got 4.0019. So if we do it backwards, if we multiply 512 by 4.0019, we get the 2000. Look, 512 divided by 128, we actually get a 4. So for 128 times 4 gives us this number. But let's go backwards again. 128 divided by 33, we actually get 3.87. So 33 times 3.87 gives us 128. You see what I'm doing? I'm just doing it backwards because it's easier for me. And the last one, 33 divided by 8, that gives us 4.125. So notice we are multiplying to go forward. But what would you say would be the most closest answer to the multiplication? I would say 4. I would say you're multiplying more or less 4. So because this is an exponential growth, it's getting bigger and bigger way too fast. Remember the formula? It's y equals the initial times the parentheses common ratio to the power of x. So what do we start with? When x was 0, once again the years, so my x was 8. So we started with 8 and the branches. We multiply by what we're multiplying over and over. We're multiplying it by 4. And that's basically the equation for the exponential growth. We know that's exponential. And we know it's growth because it's growing. We're not losing, we're getting more and more. That's the difference between a linear and a growth function.